Okay, in section 7.5 we're going to discuss a process we call linear programming. Okay, it's a method for solving problems where we want to find a quantity that needs to be maximized or minimized and it's limited by other factors. Now, whatever we want to minimize or maximize, what we're going to try to do is write what we call an objective function. And this is just an algebraic expression in which two or more variables describing a quantity that can be minimized or maximized. Okay, so we're going to look at an example of this process. Okay, so the first part is generally trying to write an objective function. Okay, we have in this case bottled water and medical supplies that would be shipped to victims of an earthquake by plane. Each container of bottled water will serve 10 people. Each medical kit will aid 6 people. And we want to let X be the number of containers of bottled water to be shipped and Y be the number of medical kits. So we're going to write the objective function that describes the number of people that can be helped. Okay, so ultimately again 10 people can be helped by each of these bottles of water containers that we bring, so 10x would be the number of people that can be helped by those. 6 times y is going to be the number of people that can be helped by the medical kits. And ultimately, when we write that down into this form, okay, the total number of people that can be helped would be the addition of those two. Okay, and we don't know how many people can be helped overall. That's what we're going to try to determine. And ultimately, we're going to let that equal some other variable. They chose z in this case. Okay, you don't have to use z if you don't want to. You can use whatever letter you choose. If you want to use P for people, okay, whatever you choose. Okay, but ultimately this is our objective function. Now, ultimately there are going to be some constraints here because there could be there's 3 variables here. So no matter what we put in for x or y, we're just going to get a z. That's not going to tell us about a maximum or a minimum. So there's going to be some other constraints given. Okay, the first constraint. Okay, before we give the constraints, let's look at the example of a constraint. Or a definition of a constraint. It's expressed as a linear inequality. A list of constraints forms a system of linear inequalities. Now, in the case of bottled water, okay, one constraint here would be x has to be greater than or equal to 0. Okay, because it doesn't make sense to have a negative amount of containers of bottled water, nor does it make sense to have a negative amount of medical kits. So we'd have those two as our constraints. Okay, and then generally we're going to be given either one or more other constraints. Like in this case, they tell us that each plane can carry no more than 80,000 pounds. Okay, and the bottled water containers weigh 20 pounds, and the medical kits weigh 10 pounds. And what we want to do is write an inequality that describes this constraint. So on the next slide, we'll see that inequality. And remember, we said that it's 20 pounds per container, 10 pounds per medical kit. This would give us our total weight. Okay, the plane can only take 80,000 pounds, so that therefore the total weight has to be less than or equal to 80,000. Okay, so this is a constraint in our particular situation. Okay, along with, as I mentioned earlier, x equals 0 and y equals 0. And in this particular problem, those are the only constraints. Now, in some problems, there might be more than one constraint, in which case they would give you means to find another inequality, okay, or another couple inequalities, whatever the case may be. But what we're going to do next is we're going to graph the constraints. Okay, now I've graphed the constraints right over here. Okay, the x equals 0 and the y equals 0, of course, are the axes. Okay, and less than, if I were to graph the 20x plus 10y less than or equal to 80,000, okay, I would get 0, 80,000, and 4,000, 0 as my two intercepts. Okay, and I have less than, so if I tested 0, 0, it would be true. So I would test in my region. Okay, my feasible region, we call that, is going to be that. Now, once we get the feasible region drawn, then what we want to do is test all the corners of the feasible region, because the corners of the feasible region are going to be where we have maximums and minimums. And remember, in this case, we wanted to know what's the maximum number of people that we can accommodate with our water and our medical kits. So we have 3 corners in this case only. Okay, so what we need to do is take those 3 corners, okay, which are 0, 8,000, 4,000, 0, and 0, 0, and plug them into the objective function that we made in part 1 of this. Okay, so when we put in 0, 8,000, we get 48,000. When we put in 4,000, 0, we get 40,000. And we put in 0, 0, we get 0. So which one of these is going to be the maximum for the number of people we can serve? It's going to be this. And what would that tell us if we were packing that plane? If we wanted to simply help the maximum amount of people, okay, we would put in no water, and we would put in all medical kits. That would serve the most amount of people, okay, under those constraints. All right. Now, in other situations, we might have a feasible region like this. We might have two constraints besides x greater than 0 and y greater than 0. Okay? We might have two, in which case if they were both less thans, we would have a feasible region that looked like this, and therefore we would have 4 points that we would need to try on the objective function. We'd try 0, 0. We'd try that point, we'd try the intersection of those two, and we'd try this point. Okay, again, when we make the feasible region, what we're going to look for are the corners of the feasible region. Okay, those are the points that are going to give us the answer that we're looking for.